And now we're going to talk about boundary layer theory for delta much less than L. So that's going to be the key argument that we're going to have. L is basically the length of the plate or the size of the object. Okay. So let's declare our system and coordinates. So imagine you have an object, maybe it might be curved, okay? Not necessarily a plate. Imagine you have these coordinates. One coordinate is parallel to the surface, the other coordinate is perpendicular, and our coordinate system is varying with the position. Okay, so x and y change continuously. So x and y, so let me define where x is the streamwise coordinate and y is the cross-stream coordinate. This x and y change continuously as you move along the boundary. X and y can be called boundary layer coordinates for flat plates, for flat geometry, flat plate geometry. X and y are the same as Cartesian coordinates. Okay, so I don't have this curved surface for the object, but I have the flat plates in that case. But in general, boundary layer coordinates differ from Cartesian coordinates. And now this is our system. Let's start to investigate. Now this is like what you would do in a fluid mechanics course. So probably, as you might remember, you start with continuity equation, you solve the continuity equation in combination with the momentum equations, x and y, and or y momentum equations. Okay, so let's start with the continuity equation, assuming fluid is incompressible, and at steady state. Okay, so it's not changing, your system is not changing with time. So in that condition, the continuity equation gives you del Vx over del x plus del Vy over del y is equal to 0. I'm not saying that just because it's incompressible you can use the continuity equation. I'm saying that you write down the continuity equation, then after some simplifications, assuming the fluid is incompressible, meaning that rho is a constant, and at steady state, meaning that you don't have this del V over del T terms in the equation, you get rid of them. After all those simplifications, your continuity equation simplifies to this form. Okay. Now, let's do an order of magnitude estimation. An order of magnitude estimation gives the following. This one is in the order of Vx infinity divided by L. So this is in the order of V infinity. This is in the order of length. So this derivative is in the order of Vx infinity divided by L. Plus the second term is in the order of Vy infinity divided by delta, right? Because y is in the order of delta, because I'm particularly interested in the range where y is within this delta region. Okay, and my x is basically like this much. So let me write through the geometry as well. So here, think about it as length L, and maybe let me not confuse the plot, but you know what the delta means, so I just wrote down what L corresponds to. L corresponds to the maximum value of the x. Okay, and from here, this sum must be in the order of 0 because it's the right-hand side of this equation. Okay. And what it means is basically Vy infinity is in the order of delta over L Vx infinity. So for delta is much smaller than L, Vy infinity is much smaller than Vx infinity. Okay. Or in other words, Vy infinity divided by Vx infinity is in the order of delta over L. Let's call delta over L as the non-dimensional delta tilde. Okay. And from now on, let Vx infinity is equal to V infinity. So I'm going to actually use this V infinity in the place of the x infinity just for the sake of simplicity. But for the Vy infinity, I'm going to write it explicitly. Now, what about the momentum equation? What does it tell us? You can use the Navier-Stokes equation. And the x momentum gives you and also no need to mention that assuming incompressible steady state flow in 2D. Okay, I have the following equation: Vx del Vx over del x plus Vy del Vx over del y is equal to negative 1 over rho del p over del x. If you want to include the effect of the gravity as well, there is rho g term, or maybe when you divide by rho, you have the gh term, but you can combine it with the pressure and you can call it like the modified pressure, and you can use some of the sources use the like fancy p for that. So instead of including the gravitational effects, you can actually dump all those into the p, and you can call a new variable called fancy p. Okay. Plus nu, kinematic viscosity or momentum diffusivity, in other words, times del square Vx over del x squared plus del square Vx over del y squared. Now we want to simplify this equation using some order of magnitude estimations, but let me first non-dimensionalize this equation, okay, by dividing both sides by the V infinity square divided by L. As I said, V infinity is Vx infinity, V infinity squared over L. So we basically non-dimensionalize by dividing by V infinity square over L. Okay. We get the following. Instead of Vx, we have Vx over V infinities. So Vx over V infinity, let's call it Vx tilde. Okay, so the Vx tilde is Vx over V infinity. Okay, so called Vx tilde Vx over V infinity. And Vy tilde is Vy over V infinity, right? And P tilde is P tilde divided by rho V infinity squared, non-dimensional, and x tilde is x over L, and y tilde is y over L. So your equation becomes Vx tilde del Vx tilde over del x tilde, right? Plus Vy tilde del Vx tilde over del y tilde is equal to minus del P tilde divided by del x tilde plus now nu, so you get what? Nu over, I guess, LB infinity, nu over L B infinity, because I guess one of the V infinities are going to get inside of the parentheses, so you're going to get del square V x tilde over del x tilde squared. I use two L's, like L squared, L times L for the parentheses. That's why I have one of the L's in the denominator. Plus del Vy squared, del square V y tilde divided by del y tilde squared. There you go. So that's the non-dimensionalized x component of the momentum. Okay. Any questions so far? No? Okay. Now we're going to do an order of magnitude estimation. As you can see, Vx tilde is in the order of 1. This O, like fancy O, means in the order of. In the order of 1 means Vx is in the order of V infinity, so Vx divided by V infinity is going to be something close to 1 for our equation. Okay. And the derivative of Vx tilde with respect to del x is going to be in the order of delta tilde, because so if you have a look at the x tilde is equal to x over L, right? So x is in the order of delta. That's why. Okay, so let's see. Del Vx over del x tilde. Okay. Vx tilde is in the order of, so let's see, Vx tilde is in the order of 1, so that's correct. But del x tilde, so that's in the order of x over L. Oh yeah, okay. X. Okay. Okay. The x, it must be in the order of L. Okay, so we should think about, so here it is. So we have a boundary layer, right? And this is your V infinity. Oops. Imagine that this is your V infinity, right? And it takes the value of Vx, okay, after a distance of L. Yep. So V infinity to Vx, and the x changes in the order of L. So basically, Vx over del Vx over del x will be in the order of V infinity, because this goes to this becomes almost 0. So you get something like V infinity divided by L. And oops, del Vx tilde over del x tilde, you basically divide by this one by V infinity and this one by L. Oops. Okay, somehow I cannot recover the thing that I found yesterday. Okay. Takes L of a distance. Takes, okay, so del Vx over del x should be in the order of V infinity okay, so let's imagine that these things happen very quickly, and let's focus on this region, very entrance region, where you have this V infinity is just immediately going down to 0. Okay. Um, why? Yeah, I guess that must be 1, right? So probably it's in the order of 1. So let's see. So I'm doing something wrong here. Okay. might be a good idea to go back to the original equation. So, okay, so let's forget about this for a moment. The Vy tilde has, if you have a look at this is the Vy tilde, and it's in the order of delta tilde, as you can see from the continuity equation. Right? And this thing, del V, oh, so that's correct. So okay, so basically I have been looking to my like y component momentum. So this is 1. This is in the order of 1, as I said. Okay, so Vx tilde scales with V infinity divided by V infinity 1, and x tilde is in the order of x over L, which is L over L, so it's in the order of 1. Okay, so that makes sense. And Vy tilde is in the order of delta tilde from continuity equation, right? And del Vx tilde divided by del y tilde will be in the order of 1 over delta tilde. Tilde. Because Vx tilde is in the order of 1 and y tilde is in the order of delta tilde. Because y is in the order of delta, so y tilde is in the order of delta over L, which is delta tilde. Okay. Let's keep this blank for the moment. This quantity is 1 over the Reynolds number, if you can realize, because the Reynolds number is velocity times the length characteristic divided by the kinematic viscosity, or rho v L over mu. So that's basically 1 over Reynolds number, that expression. And let's also keep it question mark. And this one has the order of 1 over 1, which is 1. Again, like the del Vx over del x term. And this term is in the order of 1 over delta tilde squared, because y tilde is in the order of delta tilde, and Vy is in the order of Vy tilde is in the order of sorry. Yeah, for this one, the V. Okay, so this is a misprint. I'm sorry. That must be Vx, right? Here, yeah. And the Vx tilde is in the order of 1, and y tilde is in the order of delta tilde. So you have the square of it. Okay. So what does this picture tell us? It tells us the following. If you have an equation like, for example, like 1,000 here plus some 2,000 here minus like 0.1 is equal to some like 1,000 plus something you don't know. Basically, you know that this is in the order of thousands. This is in the order of thousands. You say that each term must be in the order of thousands, or it should be neglected. If there is any leading term which has the largest magnitude, the others should be dictated by that. And if you have a look at this equation, you see that this term is in the order of 1. And this term is also in the order of 1, because you're multiplying delta tilde times 1 over delta tilde. What does it mean? It means that this term must be in the order of 1 as well. And this entire thing must be in the order of 1. And as you can see, if you add the two things, and since this is much larger than this is going to be insignificant. So this one, sorry, the other way around. This one is much smaller than the other term. So this term dominates here. Right? And it's in the order of 1 over delta tilde squared. So this is in the order of 1 over delta tilde squared. Oops, I'm not multiplying them, I'm just using the dominant one, in the order of 1 over delta tilde squared. But I want this entire thing to be in the order of 1. So this Reynolds, like 1 over Reynolds number, must be in the order of delta tilde squared. Or in other words, Reynolds number must be in the order of delta tilde to the power -2. Okay, that's a very important finding. Okay. So you can say, oh, these are just, I mean, very crude rough estimations. How are you actually relying on these? Here's the thing: you can use the scaling arguments in a similar fashion as we did in the previous class, and then you can say, oh, let me double my delta tilde, let me double my, for example, Reynolds number, whatever, and you will see that if you increase one thing tremendously large, not double, maybe take 1,000 times of it, maybe like 1,000,000 times of it, and then you're going to see some discrepancy. And if you have a relation between Reynolds number and delta tilde not aligned with this one, then you're going to see some very like large discrepancies and inconsistencies in this formula. So you want this this formula of yours to be valid for all the unit systems. And what I'm saying that is, if you use like astronomically large numbers, like for example, instead of using like 1 meter, if you use 10 to 9 nanometers, right? So your numbers are going to be really large, but it's not going to be possible to keep this equation valid with the new unit system, because your numbers are going to deviate so much. Okay, that's one of the actual reasons why we actually have a trust on the scaling or the order of magnitude estimations. Similarly, from the y momentum equation, we have Vx del Vy over del x plus Vy del Vy over del y is equal to -1 over rho del ncp over del y plus nu del squared Vy over del x squared plus del squared Vy over del y squared. Before actually doing this one, I should note that since this one dominates, you can say that this term is negligible. So actually this scaling argument actually told us that you can neglect one of the terms and simplify this equation. Okay, for the y momentums, again, let's divide by not Vy infinity, but V x infinity, or in other words, we say V infinity. V infinity square indeed divided by L to non-dimensionalize the y's as well. Both sides, V infinity squared divided by L, and you get Vx tilde del Vy tilde over del x tilde plus Vy tilde del Vy tilde over del y tilde is equal to minus del p tilde over del y tilde plus nu del square Vy tilde over del x tilde plus del square Vy tilde over del y tilde. Don't worry, we're going to simplify all these things, and things are going to be more clear and simple. And let's do the similar scaling argument, order of magnitude estimations. This is in the order of 1, as we did before. This is in the order of delta tilde, right? From because the Vy tilde is in the order of delta tilde, and x tilde is in the order of 1. Vy tilde is in the order of delta tilde. Now, I recommend you to, as an exercise, to write down the original function and try to actually guess the order of magnitudes of each term by yourself at home, just as a practice, okay? And make sure you can do it. And this del Vy tilde over del y tilde has delta tilde divided by delta tilde, which is in the order of 1. This one, let's say we don't know. By the way, this we got the Reynolds number here, right? So you should have warned me about that 1 over Reynolds number after non-dimensionalization. For this one, we have order delta tilde, and this one is in the order of 1 over delta tilde. So this is much, much larger than that. So you can neglect this. Could be neglected. And this one, since this entire thing has the order of 1 over delta tilde, this one must have the order of delta tilde squared, right? As we had found before, consistent with our earlier finding. Okay, there you go. But this tells you something very important. So this must be in the order delta tilde, right? But the previous gradient of the pressure was in the order of 1. So you can say which one is larger than delta tilde, del p tilde over del x tilde, or its y component derivative. So as you can see, since this is order 1, since 1 is much, much larger than tilde, then the derivative with respect to x is much, much larger, right? So we say that the
shouldn't it be delta squared? The squared.
These ones, right?
Yeah.
Yep. Exactly. Yep. Yep. Okay. So, but yeah, it doesn't change the result. I guess that's the same. Okay. So, order of magnitude estimation gave us information about both Reynolds number and gradient of pressure, and how to simplify the equations further. Regarding pressure, we have the following. We have found del P tilde over del X tilde is in the order of 1, and del P tilde over del Y tilde is in the order of delta tilde. That means this is much, much larger. Oh, sorry, the other way around. This is much, much larger than the latter. Thus, you can neglect the derivative of the pressure with respect to y. So you can say that the pressure is a function of x only. What does it mean? It means that the pressure changes with x, does not change with y. So you can take it at any y. So let's take it at the largest possible y, and let's call it the P infinity then, right? And let's say that, like, imagine you have this, and you have this different P's at different points, right? And we have shown that it does not change dramatically in this direction, but it changed in this direction. But we say that, oh, okay, let me take the P at this point, because this P is going to be almost equal to this one. So let me take the these P infinities instead. Okay, that's the idea here. Okay, so thus we get the following. From the continuity, del Vx over del x plus del Vy over del y is equal to 0. No simplification we have made, but in the x momentum we made a simplification. Vx del Vx over del x plus Vy del Vx over del y is equal to minus 1 over rho del P infinity, or let's say d P infinity, over dx, because it's only a function of x, plus nu del square Vx over del y squared. And I neglected the del square Vx over del x squared term because of the negligible term here. I got rid of that, and I only used this one. Okay, so that's my, and I already used the y momentum equation to actually come up with the pressure dependency, so I don't need to use it again. So our main two equations are those, and we can also get an estimation for the P infinity from Bernoulli's equation. P infinity plus 1/2 rho V infinity squared is constant, right? It's where the flow is inviscid, where your fluid is away from the surface of the solid, which means you can use the inviscid flow equation, which is the Bernoulli's equation. And if you take the derivative with respect to x, you get d p infinity over dx plus rho v infinity times dv infinity over dx is equal to 0. And you know that the v infinity does not change with x, it's a constant, right, for this problem. So you find that dp infinity over dx is 0. So it's a pretty good approximate simplification. So thus our x momentum equation becomes Vx del Vx over del x plus Vy del Vx over del y is equal to nu times del square Vx over del y squared. And you have the continuity equation. Also, we also found that the Reynolds number, is equal to V infinity L over nu, as defined such, we call it Reynolds L, which means our characteristic length is taken as the length of the plate or the object, or the size of the object. And we found that it's approximately, or it's in this, it's scaling with delta over L to the power -2. It's delta tilde to the power -2. Okay. What does it say? It says, thus, the assumption delta much less than L is valid when the Reynolds number is large enough. Remember, we actually assumed in the beginning that delta is going to be much less than L, and that's how our scaling arguments went. We assumed that delta tilde is much less than 1. So that gave us this answer. So this answer must be valid when this is much less than 1. That means when Reynolds number is much larger than 1. So we are actually talking about high Reynolds number flows here. So I'm planning to go deep into these equations more, and I'm planning to solve these equations and try to find out an answer for the delta and how the velocity profile looks. And we're going to do some estimations for the drag force and so on. So let's stop at this point. The time is up. We are going to build more on top of these, but these are the simplified equations that we're planning to solve next class. And we also need to add the continuity equation here as well. So we already listed here. This is also one of the equations. And this is the second equation. So we are going to solve the two equations simultaneously. Any questions so far?
Just making sure. Tomorrow we meet at 11, right?
Yeah, tomorrow. Thank you for reminding. Yes, tomorrow we'll meet at 11. From now on, our extra help problem-solving session is scheduled for 11 to 12 o'clock on Thursdays from now on. Okay, starting from tomorrow. Any other questions? Okay, if you don't have any other questions, briefly, let me summarize what we have done. So we have learned about the concept of boundary layer thickness and the boundary layer for momentum transfer. We briefly mentioned the boundary layer for the heat transfer as well. And we said that they are pretty analogous to each other. As we'll see later, the equations are gonna be very similar to each other. And that's why we actually first have a look at the boundary layer for the momentum, and then we're gonna talk about the boundary layer for the heat transfer in more details. And we're kind of trying to understand how the heat transfer coefficient changes with the flow conditions. That's our main goal. And in this class, we actually wrote down the continuity equation and the x momentum equation and y momentum equation. And using the order of magnitude estimations, we simplified the equations, and we had an idea about what depends on what and so on. And next class, we're going to actually solve these equations, get more insight on this problem.